I can't handle spicy food. It just sets my whole mouth on fire and makes it an unpleasant, tasteless experience. Now, what if there was something that could fix this? Take it right before you eat some spice and enjoy food without feeling like you've just descended into hell. Luckily, chemistry has the answer to all of my problems. Some crazies discovered this molecule in 1994 and named it Capsazepine, after the spicy molecule Capsaicin in the azepine functional group. It's supposed to be based on the structure of capsaicin, if you squint your eyes. Though, unlike capsaicin, Capsazepine blocks the TRPV1 receptor that is responsible for the spicy feeling of capsaicin, and so other molecules can no longer interact with that receptor and give you the spicy feeling. It is also pretty potent and already blocks the receptors in relatively low concentration. It also acts on a few other receptors, like a noxious chemical receptor, so it probably tastes pretty bad. Either way, I have found a solution to our problem, and the only way to see if it works is to make it and try it out. I didn't find anything about people who have tried it before, so we're going for a human experiment type of situation here, though it takes quite a few steps to get there. But the starting material is the natural product isovanillin, which luckily isn't too exotic. Capsazepine essentially consists of two parts, which are made separately and then linked together in the end. So I will of course start with the big piece, since the other one should be very straightforward, and hopefully in the end, my mouth will be freed from the fire. Now let's get started with the synthesis. I want to preface this synthesis by saying that I absolutely blasted my way through it, so it's going to be a little rough. You will see. To start off, we have a good old Wittig reaction. So I set up a large flask with a stir bar and add in 440 ml of dichloromethane as a solvent. Then as the first reagent, I add in 20 grams of isovanillin. And as the Wittig reagent, 52 grams of methoxycarbonyl methylene triphenylphosphorane. The reaction starts immediately, and it begins to turn orange. As everything is dissolving, I flush the flask with nitrogen to keep it under an inert atmosphere, but it probably doesn't matter. I then seal it off, and leave it to stir like this for 16 hours. This reaction is the typical Wittig reaction, where the aldehyde reacts with a triphenylphosphonium ylide, also called a Wittig reagent, to form the corresponding alkene and triphenylphosphine oxide. How it works is relatively short and simple. The ylide attacks the carbonyl carbon of the aldehyde, and the carbonyl double bond attacks the phosphorus, forming this cyclic intermediate. The carbon-oxygen bond then moves to form a double bond with the phosphorus, while the carbon-phosphorus bond moves to form a carbon-carbon double bond. This results in the product and triphenylphosphine oxide, and they have essentially just swapped their parts. When I come back, it looks the same. To make sure that the reaction is complete, I set it in a heating mantle and heat it to a reflux for 2 more hours. It still looks the same afterward, and I immediately swap out the condenser for a short path distillation apparatus to distill off all of the solvent. When that's done, I am left with a dark amber colored liquid that contains the product mixed with excess Wittig reagent and the formed triphenylphosphine oxide. The triphenylphosphine oxide is difficult to remove properly with column chromatography, so it will have to be separated out first. So while we weren't looking, I added about 180 ml of the solvent ethyl acetate. Then, I add a total of 31 grams of anhydrous calcium chloride. What will happen is that the calcium chloride will slowly complex with the triphenylphosphine oxide. That complex is insoluble in ethyl acetate and will precipitate out of solution, and then it can be easily removed. But be aware that the combination of solvent and salt is very important. So a different product might need a different solvent to dissolve, and so also a different salt to get out the triphenylphosphine oxide. This takes a while to complete, so I leave it to stir strongly for a day. When I came back, it had become a white slurry. I then set this slurry up for vacuum filtration to remove all of the white precipitate, which is the formed complex and excess calcium chloride. It stays behind as a big white hard cake, which I washed with more ethyl acetate, though the cake had shrunk and got compressed, so the solvent just went around the edges. I guess I couldn't be bothered to break it up. Moving on, the solution with the product is now a yellow liquid instead of reddish. I then set up a filter again, and on top, I put some silica gel. I wet it with ethyl acetate and then filter the whole product solution through, which should get rid of excess Wittig reagent. I wash it down with a bunch more ethyl acetate, and I am then left with a clear solution, which I set up for regular short path distillation to remove all the ethyl acetate. When most of the solvent is gone, I pull a vacuum to get all the solvent out, and a yellowish liquid is left behind, which is the molten methyl ester product. Unfortunately, it is not clear, but the color isn't too bad. I will not measure the yield here, since there's probably a decent amount of residual solvent. Instead, I directly forward it to the next reaction, which is a hydrogenation. So I add 150 ml of methanol as a solvent, and then 1 gram of 10% palladium on carbon as the catalyst. I attach a two-way gas adapter, and on top, I add a balloon filled with nitrogen. On the side, I attach a vacuum pump. Then, I cycle opening the way to the vacuum pump and the nitrogen balloon several times to replace the air in the flask with nitrogen. This is to make sure that all the oxygen is gone, which could cause the mixture to ignite during the reaction. I then repeat the same process, but with a hydrogen balloon, to fill the flask with hydrogen. I leave the way to the hydrogen balloon open, so that the reaction can constantly take up hydrogen from the balloon. I keep the reaction running until the balloon no longer shrinks from hydrogen being taken up. What happens in this reaction is that the double bond is hydrogenated to a single bond. We can see how it works if we zoom in closely on the palladium on carbon, which has tiny bits of palladium attached to carbon particles. These bits of palladium can interact with hydrogen and lowers the energy required for them to be picked up by, for example, our double bond to form a single bond. The reason they are so small and distributed on carbon is that this massively increases the surface area, and so the reaction can take place at many locations. This causes the reaction to proceed normally, otherwise it would be extremely slow. It also reduces the cost, because palladium is a very rare and expensive element. Within about a day, it no longer consumes hydrogen, so the reaction should be finished. I then repeat the same steps as before with the nitrogen balloon, to get rid of all the hydrogen again. I can then safely remove the adapter without it potentially catching on fire. I take the black reaction mixture and set it up for vacuum filtration through several filter papers to filter out the palladium on carbon catalyst. The filtrate is a clear liquid, but it seems some carbon particles still slip through. Ideally, it should be filtered through sea light to remove it all directly, but then you can't collect it to recycle it. So I filtered it all through some cotton into a new flask to remove a large part of the remaining carbon particles, though some of them still stay around, but it doesn't matter for the next reaction. Like before, I distill off all of the solvent with short path distillation, and a clear liquid with some carbon particles is left behind, making it appear gray. I transfer all of it to a new flask, and the yield turned out to be 13.2 grams, which is 48%, compared to the 97% from literature. I probably lost a bunch of product while removing the triphenylphosphine oxide, and when I filtered it through silica gel, since both can soak up some of the product if I didn't wash it out properly. Either way, that's why I'm doing it on a larger scale, so that something like this does not reduce my products to 1 nanogram. Now it is time to get rid of this ester and turn it into an acid. So for that, I dissolve all of the product in 100 ml of tetrahydrofuran. Then, I add 55 ml of water and 4.62 grams of lithium hydroxide monohydrate. The mixture quickly changes color several times, which is not the greatest of signs, and I leave it to stir for a day. In this reaction, the methyl ester is undergoing basic hydrolysis to form the corresponding carboxylate salt and methanol, after which it will be acidified to form the carboxylic acid and lithium chloride. How it works is that the hydroxide ion from lithium hydroxide attacks the carbonyl carbon of the ester. One pair of bond electrons from the carbonyl double bond is then forced onto the carbonyl oxygen. In the following intermediate, this electron pair returns to form a carbonyl double bond, and instead kicks off the methoxide, because it is a better leaving group than hydroxyl. The methoxide ion is also a base, and immediately deprotonates the carboxylic acid that has formed, giving methanol and the lithium carboxylate salt. After this step, it will be acidified with hydrochloric acid to give the free carboxylic acid and lithium chloride. When I come back, it has turned a bit more orange, and the reaction should be finished. Now, like I said, the product is in its lithium salt form, and I need it in its free acid for the next reaction. So I keep adding dilute hydrochloric acid until the pH is low enough that all of it converts to the free acid. Since the free acid is also poorly soluble in acidic solutions, most of it precipitates out of solution the moment enough acid has been added. When that happens, I add about 100 ml of ethyl acetate as a solvent, which will dissolve all the free acid, but not mix with water, so the product can be separated from the salts that are dissolved in the water. I move all of it to a separatory funnel and separate these layers. I then return the water layer to the funnel and extract it 2 more times with ethyl acetate to make sure I get out all of the product. I then bring the combined ethyl acetate extracts into the funnel and wash it once with a saturated saltwater solution, which pulls out most of the water that has dissolved into the ethyl acetate. I am then left with the washed extract as a yellowish liquid, to which I add some sodium sulfate. This will absorb any remaining droplets of water to make sure pretty much all of the water is removed, so that salts or impurities that were inside it don't end up in the product. I then set up a flask in a glycerol heating bath and filter the dried extract through some cotton to remove the sodium sulfate again. I wash it down with more ethyl acetate, and I then set it up for short path distillation to remove all of the ethyl acetate. When all of it is gone, I am left with a thick, dirty orange liquid that should contain the acid product. Now when it looks as nasty as this, it doesn't really add a lot to measure the yield. So I will just forward it to the next reaction. This is what I meant by blasting through the synthesis. From this point on, don't expect purity or yields. I will make it up to you in one of my future videos, filled with analysis. The next reaction is done neat, meaning there's no solvent added. So I add an excess of the only reagent needed, which is 40 ml of benzylamine. Then I add in 10 grams of molecular sieves, which will hold on to water that is produced in the reaction and help drive the reaction forward. And maybe it also has some catalytic action, but I'm not sure. I then heat it to 150 C and I attach a condenser that will be air cooled, just to make sure that the stuff stays in. I then leave it to stir like this for 16 hours. In this reaction, the acid simply reacts with the amine to form the corresponding amide and water. First, the carboxylic acid undergoes nucleophilic attack from the amine, and like in the previous reaction, this forces the pair of bond electrons onto the carbonyl oxygen. It also returns like before, and at the same time, the hydroxyl picks up the remaining proton from the amine and is kicked off as water, which unlike the hydroxyl, is a good leaving group, leaving us with the final amide and water. When I return, it has turned black, and the reaction should be finished by now. So I take it off heat and immediately dilute it with 300 ml of dichloromethane, which will also cool it down. Now I move all of the liquid to a separatory funnel and first wash it 3 times with 1 molar hydrochloric acid to wash out the excess benzylamine. During the third wash, some stuff precipitated out, but it redissolved afterward. Then to destroy remaining acid and to take out any unreacted starting material, I wash it twice with a saturated sodium bicarbonate solution. I then wash it once with water to make sure these salts are removed, and then once with brine, which will remove most of the water that is dissolved in the organic layer. I take the washed organic layer, dry it with sodium sulfate like earlier, filter it through cotton, and then set it up for distillation to remove the solvent. When most of it is gone, I pull a vacuum to make sure it is all gone, and I am then left with a dark liquid. To clean it up a bit, I will do a quick column, which separates components based on their polarity. So I set up a column and weigh out 150 grams of silica gel, that I mix with some 95% DCM, 5% methanol, and I pour the slurry into the column. The silica is very fragile with this solvent mixture, which is very annoying. After I had put some sand on top, I tapped the column to even it out, but it completely disturbed the silica, causing the sand to sink in. So I had to reload it and handle it carefully. So that's why there's some sand mixed in my column, but it shouldn't really do anything. Anyhow, I just ran the mixture through, but the separation also wasn't really great, but it still took out some impurities. So I just take the fractions that contain my product and pour it into this dish, and boil off all of the solvent. I don't want to overheat it directly in air, so I take it off when barely any solvent is remaining. I then do the same with another fraction that is less pure than the previous, but I will still use it. Afterward, I am left with what should be mostly the product, as a sticky solid, because it still contains some solvent, but some of it crystallized out. The second fraction is definitely dirtier, but I will just use both for the next reaction. So I just dissolve both the sticky solids in a combined total of 200 ml of THF, and I then move the solutions to a new flask. Now it is time for a reduction, and for that I have crushed up and weighed out 2.6 grams of the reducing agent lithium aluminum hydride in this dish. I suspend that in 100 ml of THF and slowly add it to the flask, which produces a lot of gas. When all of it is added, I let it stir for a second and then set it in a heating block. I attach a condenser and then reflux this mixture for 16 hours. In this reaction, the amide is reduced to an amine with the reducing agent lithium aluminum hydride. How it works is that the hydride from lithium aluminum hydride can attack the carbonyl carbon, forcing a pair of carbonyl double bond electrons onto the oxygen. This binds with the remaining aluminum compound and forms a salt with the lithium, making it a favorable leaving group. A free electron pair from the nitrogen then moves to form a double bond and kicks off the oxygen with the aluminum stuff to form an iminium. Another hydride from a second lithium aluminum hydride molecule then adds to the iminium, and the double bond electrons move onto the nitrogen to form the final amine. When I return, it has turned a yellowish green, and it should be finished. I then set up a large beaker and pour in all of the reaction mixture, because I need a larger container. I then gradually add a total of 500 ml of a saturated aqueous solution of potassium sodium tartrate. At first, the added water reacts vigorously with unreacted lithium aluminum hydride. When that has all been destroyed, I can add the rest normally. The potassium sodium tartrate helps to destroy emulsions and simplifies workup, especially after having used lithium aluminum hydride. I also just added some of the excess salt, since the salt solution was quite cold, and it should dissolve better in this warmer mixture, and then let this mixture stir strongly for an hour. When I return, it has become more orange, and when I stop stirring, it separates into 2 layers. I separate them in the separatory funnel, and then take the aqueous layer and extract it twice with ethyl acetate. I then take the combined organic layers and drain out the water that was knocked out by the ethyl acetate that was mixed with the THF. I then wash it with a total of 200 ml of water, which takes out remaining THF, and then once with brine, which takes out dissolved water and turns the organic layer transparent. Like before, I dry it with sodium sulfate, filter it, and distill off all of the solvent. I am then left with an orange liquid with a very particular smell, something similar to sweet liquor mixed with decomposing fish laying on rocks by the ocean, which is a positive sign that it contains the product, since amines usually smell like fish. I will again forward it directly to the next reaction, since it should be more convenient to purify it later on. So for this reaction, I add 280 ml of the solvent acetonitrile. As a reactant, I add in 1.04 grams of paraformaldehyde. Then as the acid and the catalyst, 2.3 ml of methane sulfonic acid. I set this mixture up for reflux and leave it overnight. In this reaction, a cyclization takes place. Formaldehyde adds to the amine and it then forms a tetrahydrobenzazepine. In more detail, formaldehyde is liberated from the paraformaldehyde by reacting with the acid, trace amounts of water, and water liberated in the reaction. The amine then attacks the carbonyl carbon of formaldehyde, and one electron pair moves onto the oxygen. In the following intermediate, this oxygen deprotonates the amine. A free electron pair from the amine then forms a nitrogen-carbon double bond, and at the same time, the hydroxyl is protonated by the acid, which is kicked off as water. The result is an iminium, which is attacked by the aromatic ring, and the electron pair moves back onto the nitrogen, giving this intermediate cyclic product. But a carbocation remains. And to fix that, this carbon is deprotonated by the methane sulfonate ion. Those hydrogen-carbon bond electrons move back into the ring to restore the aromaticity. We are then left with the final tetrahydrobenzazepine product, and the acid is restored. When I come back, it has become transparent, and it should be finished, so I take it off heat and immediately add 200 ml of a saturated aqueous solution of sodium bicarbonate to destroy the acid, and this also separates it into two layers, with the acetonitrile on top. I wash it out with some water to also dissolve some of the excess bicarbonate, and then separate the layers. I return the water layer and extract it 4 times with dichloromethane to make sure I get out all of the product. I then wash the combined organic layers, once with water and then with brine. Again I dry it with sodium sulfate, filter it through some cotton, and then set it up for vacuum distillation to remove the solvent. I am then left with a residue that should contain the tetrahydrobenzazepine product. Again I immediately continue with the next reaction, which is a hydrogenolysis, which is the same method as the hydrogenation from earlier. I again use methanol as a solvent, but this time I use palladium hydroxide on carbon as the catalyst, which is said to be more effective, specifically for hydrogenolysis of N-benzyl compounds. I repeat the exact same steps as in the earlier hydrogenation, where I add in nitrogen and then hydrogen, and I again leave it to react overnight. In this reaction, the N-benzylated compound undergoes hydrogenolysis, breaking the bond between the nitrogen and carbon, giving the corresponding amine and toluene. This works the same as the hydrogenation, except now it is a single bond that is broken. N-benzyl compounds specifically can undergo this reaction, which is why it is often used to protect an amine, as it can be cleanly removed afterward. When I come back, I remove all the hydrogen and replace it with nitrogen, remove the adapter, and filter the whole reaction mixture through some sea light. I wash it down with more methanol, and then set the filter up for distillation. When all the solvent is gone, I am left with a reddish residue that should again contain the product, which I also immediately forward to the next reaction. So the only thing for this reaction is to add 50 ml of 48% hydrobromic acid. I then attach a condenser and leave it to reflux overnight. In this reaction, the amine is transformed into its hydrobromide salt, and the ether is cleaved by hydrobromic acid to form a hydroxyl and methyl bromide that escapes from the reaction mixture. How it works is that the ether is first protonated by the hydrobromic acid. Then, the remaining bromide attacks the adjacent methyl group, and the carbon-oxygen bond electrons move onto the oxygen, giving the hydroxyl and methyl bromide. When I return, it has become green, and I swap the condenser for a short path distillation apparatus, and distill off all the hydrobromic acid under vacuum. The residue is very sticky because of trapped solvent. I ended up moving it to another flask with ethanol and tried to dry it out as much as possible under vacuum. The ethanol should also have helped to remove remaining water. The color became a lot lighter when it became dry, but it is very squishy. Anyhow, this scrap should contain a product, and I set that aside for now, because now I need to make the other piece, which is the isothiocyanate. So I set up a new flask and add in a stir bar. To this, I add 100 ml of chloroform as a solvent. I then pipette in 2.74 ml of the commercially available reagent 2,4-chlorophenyl ethylamine. As a secondary solvent, I add in 40 ml of water. As a base, I add in 3.8 grams of sodium bicarbonate. I then leave that to stir for 10 minutes, so that it all dissolves. Now, I take up 2 ml of the reagent thiophosgene, the brother of the very toxic phosgene. But this one is a red liquid, not as toxic, and it smells like meat. I then just empty the syringe gradually into the flask. When that's done, I leave it to stir strongly for an hour. In this reaction, the amine reacts with thiophosgene in the presence of a base to give the corresponding isothiocyanate. How it works is that the thiophosgene undergoes nucleophilic attack from the amine, and one electron pair of the thiocarbonyl double bond moves onto the sulfur. This intermediate with a protonated amine is then deprotonated by the sodium bicarbonate, which then splits apart into CO2 and water. Then, the thiocarbonyl double bond returns, and instead, chlorine is kicked off, since it is a good leaving group, giving sodium chloride. In this intermediate, a free electron pair from the nitrogen moves to form a nitrogen-carbon double bond, resulting in chlorine being kicked off again. The nitrogen is then deprotonated by another sodium bicarbonate molecule, again giving CO2, water, and sodium chloride, and the final isothiocyanate product. When I come back, it is mostly transparent, and the reaction should be finished, so I stop stirring, and it separates into 2 layers again. I move all of it to a separatory funnel, and take the bottom chloroform layer that contains the product, and I discard the water layer. I then wash the chloroform layer once with some water, to wash out the salts. Again, I dry the organic layer with sodium sulfate, and then just decant it into a flask. I set it up for distillation to remove all the solvent and excess thiophosgene. I am then left with a yellowish liquid that is the isothiocyanate product. Now that I have that, I come back to the crab from earlier, on which I performed a regular acid-base extraction off camera to see if I could clean it up, which took out some impurities, but overall, it still looks like shit. So for the last step, I add in 50 ml of THF as a solvent and 4 ml of triethylamine as a base. I then add in all of the isothiocyanate that I dissolved in about 50 ml of THF. I stopper it and then leave it to stir for 3 hours at room temperature. In this reaction, the amine reacts with the isothiocyanate to form the corresponding thiourea. How it proceeds is that the amine is first deprotonated by the triethylamine, giving the free amine and the hydrobromide salt of triethylamine. Then, the free amine is a nucleophile that can attack the electron-deficient carbon of the isothiocyanate, moving a pair of thiocarbonyl bond electrons onto the sulfur. In the resulting intermediate, the other nitrogen takes up an electron pair from the carbon-nitrogen double bond and deprotonates the amine. At the same time, the electron pair on the sulfur returns to form a thiocarbonyl double bond, giving the final thiourea product called capsazepine. When I come back, it is brown, and TLC showed that all the amine was consumed, so I set it up for distillation to remove all the solvent. A brown solid is left behind, and I partition it between ethyl acetate and water. I then move this mixture to a separatory funnel and separate these layers. I then return the water layer, and I extract it once more with ethyl acetate. I then dry the combined ethyl acetate layers with sodium sulfate. Now I set up a glass frit and put some silica gel on top. I wet and pack it with ethyl acetate and then filter the whole solution through, eluting with more ethyl acetate. The product adheres well to the silica and is barely carried through by the ethyl acetate, while a lot of the impurities will just wash out. When it seems like most of the impurities have come through, I start eluting with 10% methanol and dichloromethane, which will carry the product down through the silica. Everything that I collected from that, I put in this flask and set up for distillation to remove all the solvents. When that's done, I am left with a tiny amount of yellowish brown residue that should contain the product, but I will have to eat it to confirm it. So I first add some water and then some ethanol to dissolve some of the product. I add a bit more water so that the ethanol isn't too strong, and then mix it around to start dissolving the anti-spiciness. I have put some of the solution into this vial, and now I will put some of it into my mouth. Bottoms up. It doesn't taste good at all, and it's just a bit foul. Unsurprisingly, since the product should also trigger noxious chemical receptors, which probably doesn't make it taste good. It leaves a bit of a weird sensation. And now, it is time to eat something spicy. For that, I have some chili flakes, so I will just put one in my mouth. It seems to weirdly work. It's just very obvious that it didn't hit all the places. So the part where I directly put the solution, I don't feel anything at all. But the tip of my tongue, a bit of the side, and the roof of my mouth are burning. Overall, the experience isn't so great, since the initial taste is bad and it kinda makes my tongue feel weird, and it took about a day for it to go away. Also, I wasn't really a fan of this synthesis and pushing all of the crude products, but I didn't die, and I guess I have gotten what I wanted, anti-spiciness. If this is what it takes, I'll just eat the spice. Maybe if someone did some human trials, an anti-spicy sauce can be made, without having to suffer. Anyhow, thanks for watching, and if you'd like to support me in making videos, check out my Patreon below. Don't forget to like and subscribe. See ya!